Okay, so we introduced this circuit element capacitors. We discussed the definition, introduced the definition of capacitance, okay, which is the measure of the capacitor's ability to store electric charge and electric potential energy. This is the definition of this capacitance, right? It's a ratio of this electric charge each conductor carries to the electric potential between them, electric potential difference between them. This is a general definition of a capacitance. And then for parallel plate capacitors, we derived a very special, very useful equation. So to calculate the capacitance of a parallel plate capacitor, just based on its geometry parameters, right? The area and the distance between these two plates, okay? And then we also discussed that if this capacitance is the ability of a capacitor to store electric charge and electric potential energy, when we make capacitors, we always want to make this C large, right? So one way is to put insulators between these two plates, okay, to make the C larger, right? We showed that it's going to actually reduce the electric field by a factor of K, which is called a dielectric constant. So it's going to increase the capacitance by a factor of K. So it's going to make this capacitance larger, okay? So that's why we put insulators between the plates to make a capacitor, okay? At the same time, it's also going to increase the breakdown voltage, which is a good thing, right? As I said, insulators, in normal conditions, they will be insulators. But if the electric field, the electric potential on them, it's going to be, it's very large, they will still break down. They will like the air, right? If the electric field, the electric potential is too large, it's going to start to ionize and begin conducting, okay? So if you want to use the capacitor to store more charge, more energy, you want to make sure it can take a very large potential difference, right? So by putting dielectrics between these two plates, it'll also can increase the maximum electric field it can take, which is called dielectric strength, okay? So that's another name for maximum electric field a material can take without breakdown. So we have a table on slide 10 with these dielectric constants and dielectric strength for different materials. Now we're going to take a look at an example, okay? We're going to use some numbers. It's always easy to see the difference, okay, with some numbers with or without dielectrics. So let's take a look at the example on slide 11. So we're going to first calculate the breakdown voltage and the maximum charge the capacitor can store without any dielectrics. Then we're going to put some dielectrics in this capacitor. We're going to see the difference it makes, okay? So this is just a normal capacitor, right? Nothing between them, only air between them. So we want to find the breakdown voltage of this capacitor, and then the maximum charge this capacitor can store. How do I find the breakdown voltage of the capacitor? That's the maximum electric potential it can take, right? So you can only connect it to a voltage lower than this breakdown voltage. Otherwise, it's going to be damaged. It's going to become the space between them is going to it's going to start conducting. So it's going to discharge. You cannot store charge for you anymore. Okay, then how do we find this breakdown voltage? That's just the Vmax this conductor this capacitor can take, right? And then if it's a parallel plate capacitor, the potential difference between them, okay? We do have a very nice equation to connect the potential difference between them with the electric field between them, right? That's the equation we learned. So, and then if the distance between these two parallel plates, in this problem aluminum and electrodes, it's 0.5 millimeter, right? Then how do I find the maximum voltage it can take, the maximum potential difference you can apply to this capacitor? All you need to do is just find the maximum electric field air between them can take before it breaks down, before air even becomes a conductor. So this is just going to be E max times D, right? So what is E max? E max is this thing we call dielectric strength, okay? It's a fancy name for E max. Any material can withstand without breakdown, right? Take a look at the previous slide. So now I'm going to need the E max for air. So that's going to be dielectric strength of air. That's 3. So for air, E max is 3 times 10 to the 6 volts per meter, or newtons per coulomb. They are the same unit. Okay, right? So remember, dielectric strength is just a fancy name for E max, or material can take before it breaks down, before an insulator can take before it becomes conducting. Okay. So that's how I'm going to find the maximum voltage this capacitor can take. That's the breakdown voltage of this capacitor. You can never connect this capacitor to a voltage higher than that. Okay, you have to make sure you connect this capacitor to a voltage lower than that so it can function normally. Now once you have that, how do you find that? And that's it. That's how you do that. Okay, once you understand what this problem means, you see that the algebra is very easy. You just multiply these two numbers together. Okay, the distance given, right? 0.5 millimeter. Okay, what is the maximum charge the capacitor can store? How do I find the maximum charge? The maximum charge, the charge is connected to the C and V, right? So if I want to find the maximum charge, the C doesn't change, right? Once you have made this capacitor, the C is always a constant. So it just depends on the V max, right? So the maximum charge it can take is that you just connect it to the maximum voltage it can take, okay? And the C, it's gonna be its probability. But how do I find this C? I'm gonna use this equation to find the C, right? Because it tells me the diameter is 3 centimeters, okay? So you're gonna use the radius to find the area, okay? And the distance, the space between them at 0.5 millimeter. You see that they're already very close. Why do we put them very close? You can make the C large because these are at the bottom. Okay? So once you find the C, you multiply the C with this V max, you can find the maximum charge it can store, right? So that's the maximum voltage it can take. That's the maximum charge it can store, okay? All right, so now you can pause the video, find the two numbers. All right, so for the air, we found that because air, the E max is this, right? So the V max, okay, I'm just going to write it here. And the distance from the problem is 0.5 millimeters, so multiply 10 to a third. Yes. So this is 15,000 volts. What does it mean? That means, okay, if you want to use this capacitor to store charge and energy, make sure you connect it to a voltage lower than this. Okay, if you connect it to a voltage higher than this, so the air between them, it's going to break down, it's going to start conducting. So it just, if you put charge on this capacitor, it's just going to get discharged. Okay, it can even damage this capacitor. Okay, now what is the maximum charge it can store? Well, I'm going to first calculate the C using that, right, epsilon naught times pi r squared divided by d. The r from the problem 1.5 centimeters, right? So that's going to be 3 centimeters in diameter. You put them together, the C I found, okay, it's 1.25 times 10 to the negative 11th farads. Okay, so that's a typical number. As I said, the capacitance we have in everyday life is very, very small number. Okay, you can't get like 1,000 farads or something. And then you multiply this by this, what do you get? You will get 1.875 times 10 to the -8 coulombs. All right, so that's the maximum voltage it can take, and then the maximum charge it can store, right? Now we're gonna put some dielectrics between these electrodes, parallel plates. Now let's see the difference it makes, okay? So let's see, the next part. If the space between the electrodes is filled with Teflon, okay, we still want to find the breakdown voltage and the maximum charge it can store. The breakdown voltage is still gonna be this, right? But now I'm gonna use the Emax for Teflon, right? So for Teflon, what is the maximum electric field it can take before it breaks down and start to conducting? Teflon in normal conditions is an insulator. Okay. Take a look at the table on slide 10. Teflon, the dielectric strength, right? Emax is just dielectric strength. 60 times 10 to the 6 volts per meter. So it's going to be 20 times higher than air, right? So then the Vmax is still going to be Emax times D. Okay, so that's how I find the maximum voltage, the breakdown voltage of this capacitor, right? Then how do I find the maximum charge this capacitor can store? By putting Teflon between these two plates. You still do this, right? C times Vmax, because C is going to be a constant. C doesn't change, even if you connect it to a large voltage. But this C is not going to be this C, right? So you shouldn't use this value, because now you put Teflon between these two plates. We learned that that's going to change the C, right? I raised that equation. The C is going to become the factor dielectric constant times the C naught, which is the epsilon naught times A divided by D, right? So this C you calculate, you can't use that number, because now you have changed something in this capacitor, right? You put Teflon between these two plates. So the C you use is just going to be K times epsilon naught times the area times D. Okay? So that's going to be the C you use. And then you're going to use this new C, and then this maximum voltage you found. You can find the maximum charge this capacitor can store. Okay? Now you can pause the video, do the algebra. Now this is easy, right? The distance is still the same. You multiply them together, it's going to be 3 times 10 to the 4 volts. So it's going to be 20 times larger than this. Okay? So now if you put Teflon between these two plates, you can use this capacitor in a voltage larger than this, right? Like 1500, if you only have air between them, nothing between them, you cannot use that higher than 1500. Like if you want to connect it to a 2000 volt voltage source, no, it's not going to work. It's going to damage this capacitor. But if you put Teflon between them, yeah, that's fine. 2000, fine. 5000, fine. Right? You can still use that. So that's one reason, right? By adding this Teflon, the dielectrics, and this capacitor, you can raise the maximum voltage. It can be connected. Now, what about the charge, right? Remember, you're going to calculate the C. So the C is you're gonna need this K, this dielectric constant for Teflon. That's 2.1. Right? So it's going to be 2.1 times this number. You already found this number. Right? So epsilon naught times that. This is the C naught. You can call it C naught. This is a new capacitance you're going to use. Then you multiply them together. You should get 7.875 times 10 to the -7 coulombs. All right, you compare them, you see that this is about 60 times larger, right? So by putting Teflon between these two plates, you increase the maximum voltage it can take, can be connected to. you also increase the maximum charge it can store by a factor of almost 16, about 60. Okay, so that's the point. That's the point. Okay. Now we're going to move on to the next PowerPoint. Okay, so that's all, everything about one capacitor, right? But if we make a circuit, usually we have a lot of elements, right? So you're not going to just have one capacitor in one circuit. Okay, so usually in real life, the circuits can be really complicated. Okay. So you may have a combination of capacitors. How do we work with combination of capacitors? Okay, so that's what we're going to learn now. So there are actually two fundamental ways to connect circuit elements. Okay, you probably already know these two ways. They're called parallel and series. Okay, and series. Okay, what is parallel connection? What is parallel connection? Parallel connection is when you connect these two elements to the same 2 points. Okay, so if I want to draw a circuit, okay, with two capacitors connected in parallel, I would draw it this way, right? And then if I connect them to a battery to charge them, okay. So this is the symbol for a battery. So we still use two vertical lines, but we make one longer, the other one shorter. So the longer one is the long one is the positive terminal. The short one is the negative terminal. Okay. So that's a parallel connection because you see that both of them are connected to these 2 points, right? If I call this A and B, this C1, let's say, connected to C, A, and B. C2 connected between A and B, right? Both of them are connected to the same 2 points, A and B. Okay, so they're in parallel. Okay. So what is the connection between them? Okay, so we want to find some relations between them, so that can help us work with them in parallel. So and we also want to find equivalent capacitance. So if there are like many capacitors in parallel, okay, it would be nice if I can replace the combination of this guy with one equivalent element in this circuit, right? So the effect of this CEQ, let's call it, it's gonna have the same effect in this circuit. So the battery is not going to notice any difference if you connect it to this C1, C2, or another CQ, which has the same effect as these two guys. That's the point. Okay? That's why we call it CQ. So that's another thing we want to find. Okay, so let's see. How do we find this CQ? How do I find the relations between these two capacitors? So first of all, take a look at the voltage, the potential difference on this. So voltage is just another name for potential difference. Okay, in circuit we call it voltage a lot. Okay, so the voltage on C1 and C2, obviously, because they're both connected to A and B, right? Remember, voltage is just potential difference between 2 points, right? Point difference is always the something between 2 points. Difference between C1 is connected to A and B, so the voltage on C1 is going to be the potential difference between A and B, right? C2, it's also between C and B, A and B. So the potential difference, the voltage of C2 is going to be the potential difference between A and B. So obviously they're going to have the same voltage, right? So that means if I call the voltage on this guy delta V1, the voltage on this guy delta V2, or potential difference, V1 and V2, they should be the same and should be equal to the total voltage they get from the battery, right? Now you see that the battery is going to have its own voltage, and the voltage is going to be applied to A and B, right? So A is connected to the positive terminal, B is connected to the negative terminal. What is the potential difference between A and B? That's just going to be the potential difference between these two terminals because they are connected directly to the terminals. So of course, the potential difference between A and B is going to just be equal to the potential difference, the voltage they get from the battery. Okay, so this is obvious. Now, then the charge, okay, what about the relation between the charges? So they have the same voltage. And this guy is going to have Q1, this guy is going to have Q2 charge. How did they get the charge? How do they get the charges? C1 gets the charge from the battery, right? So the battery is going to provide some charge. It's going to charge this plate positive and the charge this plate negative. All of the charges come from the battery. Now C2 is going to be charged by this battery as well, right? Because C2 is also connected to the battery. So that means the battery is going to provide C1 with its charge. It's going to provide C2 with its charge, right? So that's going to be the total charge this battery provides to this combination, right? The battery doesn't know how many capacitors are connected to it. The battery is just going to provide some charge to this circuit, right? But each of them is just going to get a part of the charge. So the total charge from the battery, it's going to be the sum of the first charge and the second charge on each capacitor, okay? Now I'm going to replace these two capacitors with one equivalent so that this guy, first of all, this circuit is simpler. I'd like to work with this circuit instead of that. Secondly, if this circuit, in this circuit, the CEQ has the same effect of these two guys, the battery doesn't notice any difference, then I would just work with this circuit. I don't need to worry about that, right? But I just want to find the relation between C1, C2, and CEQ, okay? So take a look at CEQ, okay? So if CEQ is connected to the battery is going to have still the same voltage, right? It's still going to provide the same charge to the circuit, right? If we assume they are totally equivalent, right? Now in this case, all these charges are going to be on this CEQ, right? So the CEQ is just going to get Q total on each plate, right? This plate gets a positive Q total, this plate gets negative Q total, but all the charges are from the battery. So that means if I use the relation between CEQ and V on this CEQ, I should get this, right? CEQ is going to be equal to the charge on it, on each plate, which is going to be Q total. It gets all the charge from the battery because this is the only guy in this circuit. It also gets the whole voltage from that battery. Okay, so this should be the relation between these three numbers, okay, if only one capacitor is connected to a battery. Now I can make use of these two equations, right? So if I write this guy as a sum of Q1 plus Q2 and then over V total. Now because I have one number as the denominator, I have two numbers as the numerator added together. So I can actually split it up, right? So this is just going to be Q1 over V total plus Q2 over V total. And then don't forget I can make use of this relation, right? V total equals V1, V total equals V2. Okay, nice. I'm going to replace this with V1. I'm going to replace this with V2 because they are equal. All these three V's are equal. Why do I do that? Now you see that if you do Q1 over V1, what do you get? You do Q1 over V1, you just get C1, right? Because these three numbers on this C1, the first capacitor, they're going to obey this relation. So it's going to be C1 plus, and then if you do Q2 over V2, you get C2. So nice. So that means if I have two capacitors connected in parallel, okay, and I want to replace them with the equivalent capacitor, I would just draw a circuit like this, and then this CEQ is just going to be C1 plus C2. So whatever these two numbers are, I add them together, that's going to be the value of the CEQ. Then I can just go ahead and work with this circuit, okay, if I want to find anything. Okay, so that's how we find the equivalent CEQ and the relation between these V's and the Q's. All right, so that's the theory for capacitors in parallel. Now another way to connect these capacitors is in series. So what does series mean? So I'm going to erase this because we have already finished this. So this is just going to be C1 plus C2. Of course, if you have 3 of them in parallel, you just add 3 of them. Now, series is this. You have these 2 capacitors. Let's just still use 2 connected one after the other, okay, and forming a single path. Okay, you see that there's only one path connecting them, and the path doesn't split. That's called a series. So it's definitely different from that. Okay, it's definitely different from that. Okay. Now let's see. I still call this C1, C2, and I still want to figure out the relation between Q, V, and C. And also, I want to find out if I want to replace these 2 guys with an equivalent so that I can simplify the circuit I get. So what is the relation between CQ and C1 and C2? Okay. Now let's see. V1 and V2, you see that they're connected one after the other. So if I call this A, this B, okay, so this combination is going to get the total voltage from the battery, for sure, right? But each of them is going to only get part of that, right? Because this guy is not connected to A and B, only connected to A, but is not connected to B. C2 is connected to B, right? So that means each of them only gets part of the voltage, but the total voltage between A and B should be equal to the total voltage from the battery, okay? So each of them only gets part of the voltage from the battery, but if you get them together, you should get a total voltage, okay? Because this combination is connected directly to the battery, okay? So that's the relation between the voltages. Now what about the charge? Okay, now let's take a look at how these 2 capacitors get their charge. Remember, this plate is directly connected to the battery. So all this positive charge on this plate is from the battery. And then these charge, they cannot cross the gap between them. Remember, there's a gap between these plates, right? That's how you make a capacitor. You don't have them in contact, otherwise they're just going to get discharged, okay? Excuse me. So that's going to be Q1, and the Q1 is totally from the positive terminal, right? And then the negative terminal is connected to this guy. So this plate gets negative charges from the negative terminal, okay? So if this is Q1, this is Q2, both of them gets charged from the battery, okay? And the charge from battery is a charge separation. It's not the battery is not creating charge, right? So it's going to provide the same amount of charge on this plate positive, the same amount of charge on this plate negative, because it's only connected to these 2 plates. It doesn't know what's going on between here, right? It's just going to provide the same amount of charge on this plate and this plate. But if this is called Q1, this is called Q2, they should be equal and should be equal to the total charge from the battery. So the battery is going to provide positive Q total to this plate. So that's why it becomes Q1. The negative plate is going to provide negative Q total to this plate. It becomes Q2. But that's why these 3 charges are equal. Okay? Then you would say, how did these 2 plates get their charge? Because they're not directly connected to the battery. That's still a charge separation, right? Remember, these 2 plates, they're connected. So if this is a positive plate, this becomes negative, there will be a very strong electric field in this direction caused by this plate and this plate, right? So that's going to separate the charge in this region. So positive charges are going to be pushed in this direction, and negative charges are going to be pushed in that direction or attracted to that direction. So at the end, this plate is going to get some negative charge, this plate is going to get some positive charge, okay? But these charges, they don't come from the battery directly. They are charge separation in this region because they're connected, okay? All right, so that's why Q1, Q2, and Q total, they should be equal. Now, okay, we figured out the relations between the charge and the voltage. So you see that that's pretty much like parallel backwards, right? All right, it's very interesting. Now, what's the relation between C1, C2, and CQ? Okay, if I replace those two guys with this diagram, I would still have V total totally on this guy, and then Q total totally on this guy. So this guy still gets V total from the battery because it's the only guy connected to the battery, and Q total from the battery. Now, so CEQ is still gonna be Q total over V total for sure, because that's the definition of capacitance. Okay. Now let's make use of these two relations. I know that V total equals V1 plus V2, so I can replace this for the first step. So I want to split them so I can connect them to C1 and C2 only. But if they're the denominator, you cannot split them, right? But if you take the inverse, so that's the trick, right? If I take the inverse, what do I get? I would get V1 at the top plus V2 over Q total at the bottom. Now you can split these two numbers, right? Now you will get V1 over Q total plus V2 over Q total. Okay, now I can make use of this, right? So Q total equals Q1, so let's do this. Q total equals Q2, let's do this. Why do I do that? Now you see that this term only has everything about C1. This thing only has everything about C2, right? What is this? This is just the inverse of Q over V, right? This is V over Q, so that's going to be equal to 1 over C1. The inverse of C1. This is going to become inverse of C2. Okay, so the relation between them is going to be this, right? 1 over the CQ equals 1 over C1 plus 1 over C2. All right, so these are the theories we derived. For capacitance in parallel, that's the theory, right? I hope that's easy to understand. And then this is going to be the theory for capacitors connected in series, okay? So you definitely need to remember these two theories. These two theories, they're not going to be given, but it's easier to remember them if you understand them, right? So think about it, right? If they're connected in parallel, obviously the voltage is going to be the same, right? By looking at this diagram, it's intuitive to me. So if the voltage is the same, so the charges add. So that's how I remember that, okay? The charges add. And then once you remember this, just remember in series is pretty much like this backwards. So voltage is equal, charges add. Now series, so charge is equal, voltage is add, okay? And then, well, that's something you need to remember. Okay, this guy, you just add them together. This guy is going to take the inverse. And once we have reached the resistors, we're going to do the same thing again, okay? All right. So now that's the theory for parallel and series. But you don't always, if you have a real circuit, you don't always have everything in parallel, everything in series. You may have a combination of these two combinations. You would have some capacitors in series. You would have some capacitors in parallel, right? So that's a very classical problem in this part. When you have a complicated combination of capacitors, okay, how do you simplify the circuit, okay? So that's what we want to practice. So take a look at the circuit on slide 5, okay? So we have this, a bunch of 7 capacitors, okay? Some of them are in parallel, some of them are in series, okay? So how do we simplify that? Okay, so then I have 3 guys here. Now there's a battery. So I'm going to use the battery to charge all of them, right? Now, first of all, I want to find the equivalent capacitance of this combination, right? I don't like working with them, right? If I can reduce this thing to a diagram like this, oh, that's nice, right? So this is going to be the CEQ I want to find at the end, okay? So how do I simplify this diagram so that I can get that? We do that in steps, okay? That's what I always tell my students to do. Draw new diagrams, okay? And then use these new diagrams, you're going to find that, okay? How do I draw new diagrams? There's no way I can figure out everything, like figure out one equation to put all these things together, okay, by staring at this diagram, okay? I always start with some small combination I can identify as parallel or series, okay, for sure, 100%. Then I'm going to replace that small combination with their equivalent and draw a new diagram, okay, and do that step by step. Make sure I don't make any mistake. So, for example, by looking at these 7 capacitors, I don't know what to do with them, but I can definitely identify these 2 guys, this small combination. Are they in parallel or series? They're definitely in parallel 100%, right? So that means whatever the other capacitors are connected, I can replace this guy, let's call it CEQ1, right? And then it's connected to this guy. And then I still have this guy here. Now these 3 guys, I noticed that they are in parallel series. They're in parallels 100%, right? All of them are connected to the same 2 points. All of them, both of them are connected to the same 2 points. So they're definitely in parallel. So this guy, I can replace them with another one. So let's call this guy CEQ2. Right? So that's going to be the second diagram I draw, okay? Draw these diagrams, you're not going to make any mistake, okay? Then let's go from there. Okay, what about these 4 guys? What do I do with these 4 guys? I can't figure that out by staring at these 4 guys, but is there any small combination I can start with? These 2 guys, definitely in series, right? One after the other, only one path connecting them, the path doesn't split, right? If you see something, a line like this, no, they're not in series, okay? But I don't have anything like that. Take a look at these 2 guys, they're definitely in series. So that means I can replace these 2 guys with another one, let's call it CEQ3, okay? Then I would have the barrier here, I would still have these 2 guys here. Okay, and these 2 guys, I realized that they are in series as well, 100% sure. I don't care about the other guys connected to them. These 2 guys, definitely series, because the one path connecting them, one after the other. So I can replace these 2 guys, say, I call it CEQ4. Okay, now, from this diagram, how do I get to that? Well, then it's obvious these 2 guys, they're connected, both connected to the same 2 points. These 2 guys, they are in parallel. They are in parallel. I can replace that with one equivalent. Okay, that's going to be the final CQ I find. So I would always do things in steps, okay? Don't try to figure out everything using the original diagram. It's very likely you're going to make a mistake, okay? So now you can use all the numbers and the 2 theories we just derived to figure out all these capacitors to help you to find the final one. So this is 5, this is 4 microfarad, and then this guy is 6. 3, 2, 3, 7. All right, so now you can do things back step and step, okay? All right, now you can pause the video, and then do the algebra. Okay, so let's see, CEQ1. Because these two guys are in parallel, what is the theory? Oh, I add them together. CEQ1, easy, 9. Right, so this is 3, still 3, leave it there. CEQ2, parallel, okay, parallel, add them together. Parallel is easy, right? So that's gonna be 12. And this is still 6. All right? Now, series, okay, series, you're gonna do this inverse thing, right? So you cannot just add them up. So, for example, CEQ3, 1 over is gonna be 1 over 9 plus 1 over 3, right? So that's the, and then add them together. Don't forget to take the inverse again, right? Some people, they make this mistake. They add these two numbers together, they're just gonna write CEQ3 equals that number. No, you're just gonna take the inverse of this number again. So CEQ3, I got as 2.25. So this is 2.25. Now you're gonna do CEQ4, right? Okay, these two guys in series, you're gonna do this inverse thing. 1 over CEQ4 equals 1 over 6 plus 1 over 12. Because they have the same units, so you don't need to worry about units. You can just do algebra with the numbers. At the end, you just put the microfarad back. So this is going to give you 4. Okay, so this guy is going to be equal to 4 microfarad. Now, combine these two guys. Oh, they're in parallel. Parallel, nice. Just add them together. So this CEQ is going to be this plus this. The CEQ is going to be 6.25 microfarad. All right? So that's CEQ. That's how we find CEQ. Now let's take a look at the next part. Find the charge on this 6 microfarad capacitor if the voltage of the battery is 9 volts. Where's this 6? Okay, it's this guy. So I know this voltage, the battery is going to provide 9 volts. What about the voltage, the charge on this guy? Okay? Look at this diagram. There's no way you can figure out how to find the charge on this guy. Okay? This is so complicated. Okay? You don't just multiply this by this because you don't know the voltage on this, right? So that's another reason I want my students to draw these diagrams. If I want to figure out anything on a single capacitor, on a single element here, there's no way I can figure it out using this original diagram. But I can use these diagrams to go back to find things I need. Why? Okay, take a look at this diagram. If I want you to find anything on this diagram, easy, right? Why? Because there's only one capacitance on it. So the voltage is going to be 9 volts. So if you ask me, what is the voltage on this guy? Oh, that's just going to be 9 volts. What is the charge on this guy? Well, I can find it for you. It's going to be CEQ times 9 volts. Right? So that's going to be the everything about this diagram, right? But I'm not interested in this diagram. I'm interested in this 6 microfarad capacitor. Doesn't matter. Now we can go back to this diagram, okay? So we're going to do that in steps. I can use all the information in this diagram to figure out everything on this diagram. Then we're going to go back to this diagram. That's what we do, how we do that. Now, for example, this is still 9 volts, right? So this is 9 volts. These two guys, they are in parallel, so they should have the same voltage. Okay? That's a theory for the parallel circuit. If they're in parallel, they must have the same voltage. Okay, nice. So that means this guy is going to have 9 volts on it. This guy is going to have 9 volts on it, right? And then if I ask you what is the charge on this guy and this guy, so you would say the charge on this guy easy, Q EQ4 equals, because this is a capacitor, it's going to be the C times the EQ4 times the voltage, which is 9 volts, right? Because C equals Q over V, okay? So Q equals C times V, right? So if you tell me this number, CQ4, this number 9 volts on it, I can find it. If you ask me to find a volt charge on this guy, easy, okay? I'm going to still do the same thing. Q EQ3 is going to be C EQ3 times the voltage on it, 9 volts. So you see that now I can figure out everything on this diagram, okay? You would say, well, that's not what I want. But you're going to use this information to figure out things in this diagram, okay? Because without that information, there's no way you can figure out anything here. And then if you have figured out everything on this diagram, so you can go back to the original diagram, you can figure out everything on this original diagram. Charge, voltage on every single element. That's the point, right? So now let's see. If I use this diagram to go back to this diagram, so this guy, what's the connection between them? This guy is equivalent to these two guys because they are in series. That's the connection, that's the equivalent to these two guys in series. And then if I want to find the charge on each plate, each capacitor, remember the charge on each capacitor in series is going to be equal. It's going to be equal to Q total, right? And Q total is going to be the charge on their equivalent. So that means once I have found this QEQ4, that's going to be the charge on this guy. That's going to be the charge on this guy because I'm using the theory for the series connection, right? What about these two guys? The charge on these two guys is going to be equal, and it's going to be equal to the charge on their equivalent from the theory we just learned. So whatever this number I calculated on this diagram, I can transfer it to this guy. So each of them is going to have the same charge from this equivalent, right? And now you see that if I have the charge on this capacitor, I can find the voltage on it, right? Because the voltage is going to be charge divided by capacitance. What about this voltage? Charge divided by capacitance, right? What about this voltage? Charge divided by capacitance. Charge divided by capacitance. So now you will know everything in this diagram, right? So in this problem, okay, we don't need to go back because we already see this guy. I just want the information on this guy. So we can stop here. Right? But you see my point. Use all this information here, you can go back to this diagram. You can find anything on this diagram, like voltage, charge of every element. That's how you do that correctly. Okay? There's no way you can figure out anything by using the original diagram. That's why I want you to, when you find the CEQ, you go this way, use the diagrams go this way. When you want to find any information on a specific element, you go this way, you're going to find everything you need. It's going to take you some time, but that's what we're learning in physics, right? We're not learning just plug numbers into one equation ready and then enter them in calculators, okay? We're learning to do things in the right way, in a scientific way. So now you see that, what does the problem ask? The problem asks, what is the charge on the 6 microfarad capacitor? Oh, that's going to be the charge on this guy. That's just going to be this charge. How did I get this charge? Well, that's just going to be this number, two numbers multiplied together, right? You see that once you figure that out, the algebra is going to be very easy. Multiply them together. That's going to be the answer, right? And this is 9 volts, this is 4 microfarad, so the QEQ4 I can find in this problem, and this diagram is going to be 3.6 times 10 to the -5 coulombs. And the charge on this 6 microfarad capacitor, it's just going to be equal to that number. So that's going to be my answer, right? And you see that if you stare at this original diagram, there's no way you can figure out you're going to multiply 9 with 4 right? You don't even know where that 4 comes from. It's not this 4 number 4 here, okay? So draw these diagrams when you want to find the equivalent capacitance and the voltage or a charge or anything on a single capacitor. That's the right way to do that, okay? I'm going to stop here for this video.